Hello boys and girls, so in this video we are going to have our pre-lab for experiment 4, rotational motion of rigid bodies. So experiment 4, we are going to determine the moment of inertia for a fly wheel. Fly wheel is a rigid body, so you might read over the lab manual and then answer the following questions in the pre-lab worksheet. So you might refer to the lab manual page 17 until 20 for the theory, apparatus, and also the procedure of the experiment. So, introduction. Question 1. What is a rigid body? So, flywheel is a rigid body. What is meant by a rigid body? A rigid body is a body which does not change size, its size or shape when force is exerted on it. So, any body that won't change the size or shape when we apply a small considerable force on it, we consider that one as a rigid body. So, question 2. What is meant by moment of inertia? We want to determine the moment of inertia for the flywheel. So, what actually means by the moment of inertia? Moment of inertia is the tendency object resists changes in rotational motion. So basically, if greater the moment of inertia, then it will be difficult or hard for the object to rotate. So, from the moment of inertia, we might know whether the object is easier to rotate or is hardly to rotate. So, what is the symbol we use to represent moment of inertia? So, we use symbol capital I to represent moment of inertia. SI unit for moment inertia, the SI unit for moment inertia will be kg meter squared. Kg meter squared. So, moment of inertia depends on mass and also the distribution of mass. From the axis of rotation. So, this is what we mean by the statement in question 4. Let me show you. You might refer to these two pictures. You will find out that for the first one, the mass is closer to the axis of rotations, and we find out that this system can rotate faster if compared to the one on our right side. The one on our right side, the mass is further away from the axis of rotations, so it have a greater or larger moment of inertia, and we find out that the object is hardly to rotate. So, object easy or hardly to rotate, it depends on the moment of inertia, and the moment of inertia depends on the mass and also the distributions of mass from the axis of rotation. Question 5. Complete table 4 with the correct analog between linear motion and rotational motion. In linear motion, normally we consider mass when we're talking about inertia. But rotational motion, if we would like to know how easy for the object to rotate, we are going to consider moment of inertia. I. In linear motion, we are going to have acceleration A, but for rotational motion, we have what we call angular acceleration. We represent it by symbol alpha. In linear motion, for an object to have acceleration, we must have net force F. For rotational motion, in order for an object to have angular acceleration alpha, it must have net torque. Torque is the effect that responsible for the rotational motion. So, question 6. A motor capable of producing a constant torque of 100 Nm is connected to a flywheel which rotate with an angular acceleration of 1000 radian per second square. Calculate the moment of inertia of the flywheel. So we are given the torque is 100 Newton meter and it produces an angular acceleration of 1000 radian per second. So the question asks us to find the moment of inertia for the flywheel. So actually we can relate torque, angular acceleration and moment of inertia using equation torque is I alpha. So we can find the I by rearrange the equation. So we are going to have torque divided by angular acceleration. So 100 divided by 1000. So we will get the moment of inertia for the flywheel will be 0.1 kg meter squared. So this is the basic ideas about the moment of inertia for in a rotational motions. Now we proceed to the experiment. So before we answer the question about the experiment, you might read through the theory and also the procedure in your lab manual, or we can go through the instructional video about explaining the theory and also the procedure.
By referring to figure 4.1, apply Newton's for linear motion, we will obtain mg minus t equals to ma. Rearrange the equation, we will get t equals to mg minus a. And apply Newton's second law for rotational motion, we will obtain tr minus tau equals to I alpha, where a is a downward linear acceleration, tau is a frictional torque, alpha is the angular acceleration, T is the tension in the string, R is the radius of axle, and I is the moment of inertia of flywheel. Therefore, alpha is equals to RT over I minus tau over I. By plotting the graph of alpha against T, we will obtain the straight line graph as shown. The value of I can be obtained from the gradient of the graph. Therefore, I is equals to R over gradient. In order to plot the graph alpha against T, students should know to calculate the values of linear acceleration A, angular acceleration alpha, and tension T from the data taken. Hence, the linear acceleration A equals to 2h over t squared, and angular acceleration alpha is equals to A over R. Tension T equals to mg minus A, where h is the falling distance of mass, t is the time taken for the mass to fall to the floor, R is the radius of axle, m is the mass of slotted mass, and g is equal to 9.81 meter per second square. The apparatus needed are flywheel, stopwatch, set of slotted mass with hook, meter rule, G-clamp, inelastic string to hang the mass to the flywheel, cardboard, and vernier calipers. Before setting up the apparatus, make sure to measure the diameter of the axle and calculate its radius R. Now, let's set up the apparatus. Using a G-clamp, clamp the flywheel in place. Then, tie up and wound the string around the axle. Now, place the slotted mass at the end of the string. Record the falling slotted mass M. Choose a fixed point at height h above the floor. Record h. Release the slotted mass from the fixed point h and simultaneously start the stopwatch. Record the time t for for the slotted mass to hit the cardboard on the floor in 2 decimal places. Make sure to repeat the procedure 2 times to obtain the average value of time. Tabulate your data. Repeat the procedures for at least 6 different values of m. Calculate A, T, and alpha using equations 4.5, 4.6, and 4.7 respectively.
Alright, now we continue answer the questions 7 until 14 based on the video instructional video we watched just now about the theory and also the procedure. So, question 7, sketch a free body diagram for fly view and falling slotted mass. So, we find out that we are going to attach the string around the axle of the fly view, and then at the end of the string, we are going to connect with the slotted mass. So, for the axle of the fly view, there is a tension exists at the edge of the axle whereby it's at a distance r from the center of rotation. So, this tension will produce torques that rotate the fly view. So, we might refer to your lab manual. If you refer to your lab manual, so this will be the free body diagram for the fly view. So, at the edge of the axle, at a distance r from the center of rotations, we have tension T. Then it will create an angular acceleration for the fly view. Then the free body diagram for falling slotted mass. So for the falling slotted mass, it have weight downwards. At the same time, it's attached to a tension upwards. So it's accelerating downwards. So refer to the free body diagram in the lab manual. So redraw the free body diagram. So for the falling slotted mass, we have weight, tension, and the slotted mass is accelerating downward. So by referring to the free body diagram in 7a and 7b, deduce equation by using Newton's second law of motion. So for the fly view, we apply the Newton's second law for the rotational motions. So the summation of torque will equal to I alpha. The net torque will contribute or causes the angular acceleration for the fly view. So the tension acting at the edge of the axle will produce torque, whereby it can calculate by using TR. Then in real life, as the fly wheel rotates, there will be some frictional torque that oppose the rotation. So we minus the torque produced by the friction. So that one will equal to I alpha. So this is the equation for the fly wheel. Then we consider the slotted mass. For the slotted mass, we are going to have weight downward, tension upward, and then the slotted mass is accelerating downward. So Newton's second law, summation of forces equal to ma. The net force causes accelerations. So our weight is same direction as acceleration. So we are going to take weight minus tension equal to ma. Question 9. For this experiment, identify the manipulated variable and the responding variable. So you might refer to the procedure. If you refer to the procedure 3 until 7, you will find out that you need to record the falling slotted mass m. Then you release the slotted mass from a fixed height h. And then you record the time for the slotted mass to reach the floor. And you are going to repeat the step 3 to 7 for at least 6 different value of m. So the manipulated variable here will be the mass. And then the responding variable will be the time, falling time, t. Question 10. We need to complete the observation table with suitable equations. So in order to plot graph alpha against t, we need to calculate the acceleration a, the angular acceleration alpha, and also the tension that exists in the string. So the equation to calculate the acceleration, if you refer to the lab manual, in the theory, the equations we use to calculate the acceleration will be equation 4.5. A is 2h over t squared. How we get these equations, you might refer. back to the setup of the experiment. So this is our slotted mass, and we are going to release the slotted mass from a certain height h. Initially, there is no movement for the slotted mass before we release. So the initial velocity is 0. The displacement will be negative h. Why? Because the slotted mass is moving downward. So the slotted mass is accelerating downward with the acceleration negative a. So refer to the kinematics equation. S is ut plus half at squared. Our s is negative h. Our u is 0. Our a is negative a t squared. So this one 0. So rearrange, we will get our a will be 2h over t squared. So this is the equation we use to determine acceleration. Then the angular acceleration can be calculated using equations 4.5. In rotational motions for an object that rotates tangential to the radius, there will be tangential acceleration. This tangential acceleration can relate with the angular acceleration of the object, whereby we have a equal to r alpha. So we can determine the alpha by using acceleration divided by the radius of the axle. And for the tension in the string, we can determine from equation 4.1 in our theory, whereby mg minus t equal to ma. When we rearrange, the tension will be m in bracket g minus a. So tension can be calculated using mg minus a. G is the acceleration due to gravity. A is the acceleration of the falling slotted mass. Now we move on to the data analysis. Question 11. Write the equations of the graph of alpha against t. So, what is the equation in the theory that we are going to use for these experiments? So, we are going to use equation 4.3, whereby we are going to plot a graph alpha against t. So, we have the equations. Alpha is r over I in bracket times t minus the frictional torque over I. So equation 4.3, we are going to use the equation 4.3. So we are going to plot graph alpha against t. It means that we are going to plot graph alpha against t. So if we refer back to the theory in the lab manual, the graph alpha against t is a straight line graph. So we are going to compare the equation 4.3 with straight line equation. Y equal to mx plus c. So we can see obviously our y-axis is alpha, our x-axis is t. Then the gradient of the graph is represented by r over I, and the intercept of the graph will be negative, where that equivalent to the frictional torque divided by I. So we shall get a straight line graph that will have a negative intercept. Okay, so the gradient will be r over I, and the intercept will be negative frictional torque over I. Next question, question 13. How do we determine the value of inertia of a fly wheel from the graph? So how you are going to determine the moment of inertia from the graph? So if we do the comparison, we find out that our gradient is r over I. So we can relate the moment of inertia with the gradient. So we can determine the gradient of the graph by drawing a triangle, and then we can determine the moment of inertia, whereby our gradient m is the radius of the axle divided by moment of inertia. So rearrange the equations. The moment of inertia will be radius of the axle over the gradient of the graph. So r represents the radius of the axle, and m represents the gradient of the graph. Alpha against t. Okay, so this is how we determine the value of moment inertia for the fly wheel. question 14, we have to list 3 precautions of the experiments. So when we do the experiment, what precaution step we need to taken? So first, we have to avoid any external force when releasing the slotted mass. Okay, second one. So we are going to move the string around the axle. So make sure we move the string around the axle neatly. Okay, and the third one, class, if you notice, we need to record the mass of the slotted mass in the experiment. So this slotted mass is put on a hanger. So when you record the slotted mass, don't forget to add in the mass of the hook when recording the value of M. Yeah, the hanger alone have a mass of 20 gram. One of the slotted mass is 20 gram. So for example, this one, so the hook have 20 gram, then we have 2 slotted mass add in. So the reading that we should record will be 60 gram. This is the 3 precautions of the experiment. So that's it for today for our pre-lab sessions. So I shall see you next week. Thank you, class. Bye-bye.